Have you ever had to make a really big decision with, like, almost no information to go on? That feeling of just staring into the unknown, really hoping that your first move is the right one? Well, that's a huge human challenge, but it's also one of the biggest, toughest hurdles for artificial intelligence. So today, we're going to dive into how both people and machines learn to explore when the clues, the feedback, when the rewards are super, super rare.
All right, let's just jump right in with a classic. Picture a brand new game of Minesweeper. You're just looking at this grid of totally blank squares. No numbers, no hints, nothing. And yet, you have to make that first move. That one click could reveal a nice, safe path, or boom, game over instantly. Where do you even begin?
And look, this isn't just a game. It's a perfect, distilled version of a massive problem that shows up pretty much everywhere. We're calling it the first click problem. It's all about taking that first blind step into a huge, empty space of possibilities.
And this slide really breaks down why it's so tough. You're staring at this massive space of possibilities with absolutely zero clues. And the stakes are high. One wrong move and you're done. So you can't just guess randomly. You're forced to think ahead, to ask, okay, if I click here, what are the possible things that could happen next? What new information would that give me? That's hypothetical thinking, right there in its purest form. And hey, don't just take my word for it. Researchers figured this out a while ago. A study from way back in 2010 suggested that Minesweeper is way more than just a time waster. It's basically a cognitive training tool. It actually forces our brains to build and test mental models, which is a skill that is absolutely crucial for any kind of complex problem solving.
Okay, so let's zoom out from the game for a second, because this whole first click problem, it's not really about Minesweeper. It's the perfect analogy for a core challenge in artificial intelligence, trying to navigate these huge empty spaces where the right path is totally hidden.
And this slide just nails the two kinds of worlds an AI can find itself in. Over on the left, you've got dense rewards. Think of a game like Mario, right? There are coins everywhere. Every few steps, you get a little bit of positive feedback, so you always know you're on the right track. But then you have the other side of it. Sparse rewards. This is like someone telling you there's one single treasure chest hidden somewhere in an entire desert. You could wander for miles, or for an AI, run millions of simulations without a single clue telling you if you're getting warmer or colder.
And that brings us to the official term for this whole mess, sparse exploration. It's the challenge of learning to make good decisions when the world isn't giving you a constant thumbs up. This is exactly where simple learning algorithms just completely fall apart. Without those frequent little rewards, they just wander around aimlessly. They're totally lost.
So if AI gets stuck here, how do we humans solve this? Because we don't just wander aimlessly. We have this amazing built-in brain hack for dealing with these big, sparse problems. And another game, Minecraft, gives us a perfect look at how it works. I mean, think about it. If your goal is to build a giant castle in Minecraft, that's a massive, sparse reward task, right? The final reward, that amazing finished castle, is maybe days or even weeks away. You don't just run up a hill and start throwing down cobblestone blocks at random, do you?
Of course not. You use a strategy that psychologists call chunking. You basically invent your own dense rewards. First, you'll say, okay, goal 1, find a good location. That's a little win. Then goal 2, gather a bunch of wood. Another win. Goal 3, mine for stone, and so on. You break that one giant, far-off goal into a series of smaller, achievable sub-goals. You create your own path through the desert. Now, what's so cool is that this human strategy of creating our own little sub-goals, well, it has a really powerful parallel in the world of AI. Machines have their own algorithmic version of chunking, a way to systematically think ahead and find their way through the emptiness. And its name is Monte Carlo Tree Search, or MCTS for short. And this thing is an absolute powerhouse. It's the algorithm behind so many of AI's biggest breakthroughs in things like strategy games and other really complex reasoning tasks. It's how an AI learns to see the whole forest, not just the trees right in front of it. So how does this work? Well, it's this brilliant 4-step loop that just repeats itself over and over. First, it selects the path that, based on everything it knows so far, looks the most promising. Then it expands that path by trying just one new unexplored move. Next, and this is the really genius part, it simulates the rest of the game randomly from that new point, just to get a quick and dirty idea of whether it leads to a win or a loss. And finally, it takes that outcome and updates its original belief about how good that first path really was. It does this thousands, even millions of times a second, building this incredibly rich map of possibilities. And I want to be clear, this isn't just some old school theory from a textbook. This is the real deal. It's at the absolute heart of cutting-edge AI research, with frameworks being designed right now to bake this kind of systematic thinking directly into an AI's brain to get over this exact exploration bottleneck.
Okay, so games in theory are one thing, but where does this stuff actually, matter in the real world? Well, let's look at one of the most complex and maybe surprising applications, trying to make chatbots that can actually understand human culture. And the stakes here, they are ridiculously high. Just look at this number. Projections suggest that in just a few years, over 95% of all customer interactions are going to be handled by an AI. Think about that for a second. If those bots can't figure out the incredible subtleties of how we talk to each other, we are heading for a massive communication breakdown. And human culture is maybe the ultimate sparse reward environment. I mean, research shows that attitudes toward AI are wildly different around the world. For instance, East Asian cultures tend to be much more open to the idea of a chatbot friend than Western cultures are. Now add in over 100 languages, countless idioms, unspoken social roles, and you start to see that for a chatbot, a conversation is a maze. Finding the one right response that's culturally and emotionally intelligent, yeah, that's like finding that one treasure chest in the desert. And this is where MCTS becomes a game changer. It allows these advanced chatbots to do what we saw before, to systematically explore. They can simulate thousands of different conversational paths, testing out different tones and phrases, and learning from the outcomes to figure out what a culturally sensitive response actually looks and sounds like, without needing someone to tell them good bot or bad bot every single second. So this whole idea of finding a very faint signal in a giant sea of noise, it goes way beyond just chatbots. It's shaping our digital future in ways that are both incredible and pretty thought-provoking, connecting brand new tech to some very, very old ideas. Check out this amazing example from a research project in Rome. There's a system called Hufai that can identify a specific person in a room with no cameras, no microphones, no wearables. So how does it do it? By analyzing the incredibly tiny, subtle ways that a person's body disturbs the Wi-Fi signals that are already in the air. That unique biometric signature is a perfect sparse reward. It's a tiny, almost invisible pattern hidden in a massive amount of random data noise. And what's just fascinating to me is how this super modern tech, it actually circles right back to wisdom from centuries ago. The Scottish philosopher Thomas Reid argued that we never learn from a blank slate. Ex nihilo, from nothing. All of our knowledge, all of our ability to reason, is built on a chain of past experiences. We learn by standing on the shoulders of our previous judgments. And that is exactly what these systems are doing. Whether it's an AI learning from thousands of simulated conversations so it can navigate our cultures, or a system learning from past signal disruptions to identify a person, they are all building on what came before. Reid's idea of an ideal agent was something that could learn from every single experience to better navigate the future. And that's precisely the goal of modern AI. So this leaves us with a final and pretty huge question. These powerful exploration strategies are allowing AI to learn from the vast collection of our past actions, our conversations, even just our physical presence. So if AI is using our collective past to navigate the unknown, what kind of future is it charting a course toward for us? That's definitely something to think about.